So welcome to computer graphics. And so today I'm going to go over the syllabus. And what we're looking at here is a little bit of computer graphics, a little bit of OpenGL, a little bit of concepts, not too much math, but a little bit of that, and a little bit of general implementation, and a little bit of programming, and a little bit of experimentation with a lot of different graphic languages. So this class itself is going to be sort of a combination of a lot of things. The course is going to provide an overview of principles of 3D, 2D, 1D, in terms of what that means. Talk about the graphic pipeline, talk about things associated with modeling, rendering, animation, lighting, shading. Topics will focus on some of the algorithms, some of the mathematics. I don't want to turn this into a heavy-duty math class, though. I find a lot of teachers either take one direction or another. Either they focus on the transformations and all of the matrix math and all of the different calculations with that, or they focus on the graphic libraries. I have a tendency to focus on the graphic libraries and on the tools that you're going to need and on the utilities to actually implement some of these concepts. So the topics that we're going to look at are going to be related to geometric and modeling transformations, 3D viewing, projections, modeling curves and surfaces, which is kind of interesting actually when you think about it. The way that items, solid modeling is done, illumination models, texturing, texture mapping is kind of interesting as well, visual algorithms, animation, physical-based modeling. The purpose is to give you exposure to the foundation, to the terminology, to a background of it. What I really want to do, however, is introduce you to C++ and the OpenGL library. The OpenGL library is going to give you a toolkit in which you're going to be able to create some pretty fancy little worlds and things. And we're going to use a compiler called Bloodshed that is a GCC. Well, it works on a GCC GNU compiler. They'll work with Windows, no problem. And next week I'm actually going to run through the install. So if you want to bring your computer next week, you can actually get the graphics library installed. You can get the software that you're going to need installed. You don't have to be a C programmer. You don't have to be a programmer at all. It's actually kind of easy. It's not like heavy-duty programming. If you're not a C programmer, you're going to need to get a book or something to get up to speed. Do you guys know C in general? Computer graphics?
Yeah, I do.
Okay, good. I'm just making sure you're in the right room. If your background in C is kind of old, like maybe from many years ago, don't worry about it. Basic computer concepts in terms of being able to define variables and run function calls, because the OpenGL library is all about a bunch of functions. It's a non-object oriented programming environment. It is definitely easier, I would say, than most other packages. And OpenGL is usually the base language for a lot of higher level APIs. So a lot of some of the Android tools, some of the web development tools are built on top of OpenGL. So whether you're using OpenGL or not explicitly, you are probably. It's one of the most popular libraries out there. And I think instead of teaching an API on top of it, I'd rather just teach you the OpenGL, which requires a little bit of C, C++, but not actually more like just C, not C++. Because we're not going to be creating classes and we're not going to be doing any object-oriented programming. It's all basic C programming. And the way I like to teach is I like to give you a lot of examples. So next week we'll download the software, we'll download the library, you'll see how it comes together. Although I'm on a Mac, I'm going to do it on a PC. It'll be on a Windows virtual machine, so you'll see it in the Windows environment. It also works on a Mac, however, a slightly different tool set though. So I'd rather show you what most of you are going to be doing. So it assumes that you have taken some programming courses, but you don't have to be an expert. Also assumes you have a background in math a little bit, some data structures perhaps, algorithms, basic mathematics like matrix algebra. Most people at this point do. Maybe a little trigonometry might help you, linear algebra, but we're not going to focus on any of the calculations because this is what the OpenGL library gives you. When you want to create a new shape, you just tell it the shape and you tell it the coordinates that you want to create it with. It does it for you. It does all the calculations for all of the transformations and stuff as well for you. So the library is really going to do all the math for you. You don't really have to worry about it. So if you want to understand the underlying concepts, that's where the math background comes in handy. In terms of the learning outcome, knowing the basic computer graphics concepts, 2D, 3D modeling, understanding the image formation, representation, a little knowledge of the OpenGL library as well, knowledge of scan conversion methods, projections, viewing. Don't worry about it if you don't know any of these concepts. This is what we're going to learn in the course. We'll look at a little bit of ray tracing. I'm not going to spend too much time on it because ray tracing right now hasn't really been that perfected. There's a couple of ray tracing models out there. I'll introduce those to you. A little bit on animation as well. Animation you'll find is actually going to be kind of cool. It's really easy to do, believe it or not, especially when you're using OpenGL. The textbook for this course, so the required materials for this course, I don't actually require you to go out and buy a textbook. If you go online, you can find PDF versions of this. This one is interactive computer graphics, top-down approach using OpenGL. Actually, let me just do a quick search here. I can figure out how to do a quick search. Let's see. Let's go to Google. And I'm going to type this in. Here we go. Open download. Here we go. You can download it. I believe it's. Whoops, it's not going to be here. Anyway, one of these links is going to give you a download for it. It's available for free. It's an open source utility. OpenGL, believe it or not, is open source as well. So you don't pay for OpenGL as a library or a toolkit. And it's basically an open source API that can be used. This looks like a printed version of the book here. I know I can, if I find the link, I'll spend some time. Actually, no, this is a PDF. Download converter. I know it's a converter. Here's the book right here, Interactive Computer Graphics. That's what I wanted to find, was kind of a cover for you. You can find it in a lot of different sources. I know there's a couple of different electronic versions of it. I used to have, I think I probably still have the printed version of it. You know, it can get by without the book, but if this is your first graphics course, you really want to learn OpenGL, you want to apply this towards like game programming and stuff, I recommend the book. Only because it'll teach you a lot of stuff that I probably won't cover in the class. That'll be applicable towards application development. So it's not a bad resource if you're interested in it. It's a good investment. We have an encyclopedia coverage of computer graphics. We'll also be covering very specific topics as well. It might be possible to, it's impossible to cover the entire scope of computer graphics all in one course, and especially, focusing on everything. But we're going to focus on OpenGL. And here's some other optional books. And there's nothing, this one says required, but it really isn't required. In fact, you could probably get by with no books for this course and use internet websites, internet resources. If you just go open up a web browser and type in OpenGL, you're going to find a ton of tutorials, a ton of PDF files going through all of the different libraries. But these are the ones I've actually kind of used and I'm familiar with that I would recommend. So most students are interested in finding out the grading, so that's an interesting part. So the course is broken out into 4 different categories. We've got a final exam at the end of the course, which was 25% of your course grade, and it's comprehensive, and it will be an in-class assignment. And the final exam will be given during final exam week, which will probably end up being the first week in December-ish, is what I'm thinking. We also have this thing called a CSLO essay, and the CSLO essay is an essay assignment. It is, it's not, if you don't submit a student, you will not receive a grade in this course. Yes, you will. You'll probably get a low grade, but you're not going to get a good grade. So the CSLO essay is going to be a writing assignment, 2 to 3 pages. We're going to pick a topic that's related to graphics, and I'm going to give you a list of the topics. In fact, if you go out, if you're brand new, probably should mention the website. Have you guys all taken classes with me before? You know, it's hard to tell who's new and who's not new. And if you go out to the website, I believe I have the midterm and I also have the CSLO out here. Nope, I don't. Ooh, I have to populate that. So I'll put that out here soon. What we're looking at in terms of the CSLO is going to be an activity for which you're writing something. You also have 5 hands-on assignments that you'll be doing that are worth 5% or 25% total, We also have a midterm, as I mentioned before. It will be a take-home exam. So the midterm will be take-home. The assignments are take-home. Finals in class, CSLO is take-home. It's 25, 25, 25. The assignments should be out here as well. All of this stuff will be populated in the, here's the assignments, in the EMS fairly soon. The EMS, or the LMS, is not really ready for it yet, so we're working on getting the materials in there. But the assignments themselves here have a bunch of supporting links that go with it. You'll find everything right now. In fact, even after the LMS gets populated, you can still find it here. So you can still come here and take a look at this stuff. But you'll also see, not on here yet, but video recordings, because I'm recording each one of these videos, or each one of these lectures. So programming example is going to give you a bunch of OpenGL and C++ stuff. So, but we'll see Hello World and OpenGL next week. We do that. So, not a bad idea to bring a computer next week. And you also notice in the lecture series, I've got some lectures that are, let me guess here, there's like 42 lectures, perhaps, plus a bunch of other OpenGL type lectures. I'm not going to cover all of these lectures, all 42 of them. That would be a 42. That would be like a year course. So some of them are OpenGL related, some of them are computer graphics related. You can go through and you can find topic by topic. I've been meaning to actually put some descriptions out here, because then these lectures actually can be a really good substitute for a textbook. And it would be nice to know which one of these, which they were all about. So I'm thinking about, in the future, putting some explanation out there, maybe some listing. Not a bad idea. So students know what they're all about. Some of these other ones are color, like color, lighting, view, shading. I'm going to go through a lot of the different ones per topic. So, and the topics that I'm going to go through are actually listed in the syllabus at the end. So if you go to the end of the syllabus, also downloadable from bafter.com, you'll see a week by week listing of the topics. Example, this week is an overview, introduction to computer graphics. Next week is going to be computer graphics systems and modeling. And then we're going to go into graphic programming, input, interaction, geometric figures, things of that nature. As you might notice, especially if you're new, there's no due dates listed. It says weeks, like week 3, week 4, week 5. But don't panic if you can't submit something. Nothing is really due until the very last day of the course, as always. This just says in class. It's not going to be in class. It's going to be a take-home, so don't get freaked out by that. I have done the midterm in class before, but I think this term I'm going to do a take-home, so it makes it easier. Although I probably should do it in class. I'll get more attendance that way. I don't know, maybe I'll change my mind. Who knows? I don't know. Probably not. It'll be take-home. Questions about anything that I've covered in the syllabus in terms of how the course is going to be run? And for those of you who came in late, we're going to start the course. Actually, it looks like I have extra time here. For those of you who came in late, we're going to start the course at 5, because a lot of people have to take the bus and they end up having to leave at 6:20, which is how I'm going to try and get us out at 6:20 today, actually. Which means I have time, because it's only 6:07, so we can go over lecture 1, I believe. We have time for that, unless there's questions about the syllabus. Nope, no questions about the syllabus. Moving right along, which is kind of like the first day orientation anyway. I always let everybody out the first day early anyway. So let me briefly go over in the next 10 minutes or so, which is perfect timing actually. This is a very small lecture. Some more topics for which we're going to cover, and kind of an orientation to the concepts that we're going to look at in this course. In terms of computer graphics, so we're going to explore the concept of graphics, do a survey of some of the graphic application areas, talk about some of the APIs. Start with a historical introduction. I'm not going to bore you too much in the beginning with the history of computer graphics, because a lot of it's hardware related, and a lot of it is, as monitors have gotten better, as graphic cards have gotten better, and processing has gotten better, the graphics have gotten better. Because if you think of the concept, computer graphics in general to be done on a computer, and to get the resolution, to get animation, motion, stuff of that nature, it's a lot of processing. And the processing, in the past, up until like maybe the last 10 years, hasn't really been that good. Now we have more sophisticated computer systems, faster processors, graphic cards with memories and their own processors on them. We're able to actually kind of process a lot quicker, and it creates a better experience for the user, and creates better computer graphics. A lot of the technologies have changed as hardware and software has improved. So computer graphics deals with the aspects of creating images with a computer, hardware, software, and applications. Here's an example. Where did we get this image from? Well, we had an algorithm, or we had a function, or we had something that we did that actually displayed it. So what hardware, software do you need to produce it? That's actually a very interesting question, which is like a lot of the things that go into the decision of some of the game applications and consoles that are out there. You know, how fast does a processor need to be for the motion to work correctly? What applications, what software, what utility are you going to use to actually draw it? Because what you don't want to do is just like go out there and draw it pixel by pixel or something, you know. Or here's some preliminary answers, but there's different ways of approaching the concept, essentially, of creating an image on a computer. You can use an application. As an example, the object is an artist's rendition of a sun, of an animation to be shown in a doomed environment. That's a sun, I guess so, on top of a orb thing. Software, we have Maya for modeling as an example, rendering, but Maya is built on top of OpenGL. That's why I've kind of taken the approach of showing you OpenGL. All these other packages are built on top of OpenGL. So why not learn the source? If you learn the source, then you can kind of actually pick up the packages that are using the API a lot easier in some ways. We're also looking at the concept of hardware, PCs with graphic cards for modeling and rendering. So here's your basic graphics system, and these are the components that are associated with it. You have the input devices, keyboard, pointing devices, and stuff of that nature. It goes into a processor, memory associated with it, image frame buffers, output device. It's pretty simple in terms of the architecture of what we're looking at, the basic graphics system. This is old technology if you think about it. We have LCD displays now. We have all sorts of different types of things outside of the CRT. But in the old days, we actually had a CRT. So it can be used either as a line drawing device or to display contents in the frame buffer, raster mode. So a lot of the primitive kind of graphics applications that were out on the market were based on older hardware. In terms of in fact, this slide's going back from 1950s, 1960s. If you go back that far, we're looking at strip charts, pen plotters, simple displays using AD converters. We go from computer to CRTs. Cost to refresh the CRT is too high, so computers were slow, expensive, unreliable. And then we've progressed from there. So around 1960s, 1970s, in terms of the history, we looked at wireframe graphics. We actually still do wireframing today. Wireframe graphics is still out there. You guys are familiar with wireframing at all? Done any low-level wireframing? It's actually kind of cool. You can take a picture, wireframe it, and then texture map it. You can do all sorts of different things to the wireframe to recreate it in different ways and animate it, make it come to life. And people are doing a lot of this actually right now with scanned images. So you take like a picture of somebody, you scan it in a computer, and then you can make like a robot out of that person, out of that picture by wireframing it and then filling in, texture mapping it, doing all sorts of different things to it. So wireframing in general just draws lines. This is a wireframe. It just draws the lines in terms of the structure. Sketch padding, display processors, storage tubes, so wireframe representation of the sun object in the previous slide. In terms of sketch padding, this came from a PhD thesis over at MIT, recognize the potential man-machine interaction. So we had a loop that displayed something, then the user moves, like a light pen, and the computer generates a new display that was associated with it. So it created many different common algorithms as well. So a lot of the earlier research in terms of these techniques over here have formed some of the models for the more modern techniques that we're using today in the 70s. And it has definitely changed significantly from there because display processors have changed significantly, and so have the processing of computers and the graphic cards and things of that nature. So rather than host a computer, try to refresh the display, use a special purpose computer, we ended up with a display processor, a DPU, as a concept. So we had a host with a display processor with a display list, and then the processor told the computer what it needed to run in that nature. So graphics stored in the display list, is on a display processor. So the host compiles the display list and sends it to the DPU, which is actually kind of the same model that's really occurring today in terms of GPUs, graphic processors. We had direct view storage tubes as well, created by Tektronix. Didn't require a constant refresh. Standard interface to computers, allowed for standard software, plotted 3D. It came from an older language, Fortran was used in that. Relatively inexpensive, opened the door for computer graphics and CAD community. Actually, the CAD community was fairly strong back in the early 80s as well. We had Raster from 1970 to 1980, going down our little history. We had Raster Graphics. Yeah, it was the beginning of the graphics standards in terms of what is more similar to what we're doing today. And then the workstations and PCs were starting to do graphics as well. Here's an example of what's meant by Raster Graphics. The image produced as an array, the raster of the picture element, pixels, in the frame buffer. So we had pixels in terms of an array of rasters that was displayed. It allows us to go from lines and wireframings to images to filled polygons, essentially. And nowadays we speak of polygons, and when we do wireframing, we actually draw polygons on our wireframes. I mean, everything's in this form of a polygon representation, and then you connect the polygons together and you get the image. You get the surface of the image. And we're just wireframing surfaces, essentially. And then we had the concept of PCs and workstations that were mostly like silicon graphics. Some Apple computers are actually used today for that. So although we no longer make a distinction between workstations and PCs, historically they evolved from different roots. We had earlier workstations that were categorized by network connections, and then we had earlier PCs that included frame buffers as part of their memory. So with the creation of more PCs, we had more processing that would be able to occur with more memory, more buffer space. That created more sophisticated graphics, essentially, in terms of the evolution. And then we had realism. So 1980 to 1990, realism comes to the computer graphics world. So we have the ability to apply, as an example, some smooth shading to get texture feel, and environment mapping, bump mapping, and these are all of the concepts that we're going to go over in the course. How to get this effect, what the effect is, what it's called, and the beautiful thing of all is that the OpenGL library has built-in functions to give you this stuff. You just have to know what it is so you can use it. From the 80s to the 90s, we also had special purpose hardware, and that's where silicon graphics came into play, geometry engineering. I don't know, is silicon graphics, SGI, still around? I can't remember. I think they are still around. It's like one of the oldest graphic companies out there. Industry-based standards, RenderMan, some open source stuff, network graphics, X systems, human-computer interface became popular around the 90s. Then we had the 90s to the 2000s. That's when we got the OpenGL API. So it's really not that old. Well, actually, this is 2011, so it's 10 years from 2000. I guess now that I think about it, it's like 20 years old. Okay, it is old. Completely computer-generated features. Feature-length movies. Actually, Toy Story was made by using OpenGL libraries. And new hardware capabilities. It gave you texture mapping, blending, accumulation, stencil buffers, and these are all topics we're going to talk about. From computer graphics from the 2000s onward, then we had photorealism. Well, now we have photo printers, too, that we can print out pictures with today. Graphics cards for PCs on the market, NVIDIA, ATI. Some really better sophisticated specialized graphic cards that include the features, hardware features needed to do the processing, to actually work with these programs. Game boxes, game players, basically determining the direction of the market. A lot of it came out of the gaming industry. Computer graphics routines in movies included Maya and Lightwave, and then programmable pipelines essentially came out of that as well. So what you just got was a whirlwind tour of not only the history but the direction of this course. So I believe next week is going to be all about OpenGL. So next week what we're going to do, because I'm going to cut it short this week because a lot of people got to take the bus. Next week we're going to look at the OpenGL library. We're going to install the C++ tools and the OpenGL library. And I'm going to go through the basic features and we're going to compile a hello world. So if you just came in, sign the roster, and know that next week class is going to start at 5 p.m. and that this week is the last time it's going to start at 6. And that we are going to end momentarily because of the timing of the course and the bus schedules and everything, which is why we're starting at 5 next week. So we'll probably go from 5 to 6:20, 6:30 at the latest, 6:20, an hour, hour and a half, which works out best for everybody's schedule, I believe. So, questions, comments, concerns? No? We all good? So next week, OpenGL, software install. We're going to move right, we're going to go from this orientation all the way up to looking at graphic stuff starting next week. Okay, thank you for coming. Thank you.